Hello, dear viewers. Direct experimental evidence for multiverses is difficult to obtain due to the nature of the concept. However, various indirect evidence and theoretical motivations support the plausibility of the multiverse. Some anomalies, such as the cold spot in the cosmic microwave background, are predicted to be the result of collisions with other bubble universes. Although not conclusive, these anomalies provide intriguing clues that may be consistent with a multiverse. Extreme fine-tuning of fundamental constants, e.g., cosmological constant, strength of the electromagnetic force, suggests that these values may not be unique. The multiverse offers an explanation that different regions of the larger universe have different physical constants and that we observe values that enable our existence. The theory of eternal inflation naturally leads to the creation of multiple bubble universes. If inflation occurs, a multiverse will be produced in which each bubble universe has different physical properties. The success of inflation theory in explaining the large-scale structure of the universe lends credibility to this idea. The landscape of string theory envisions a multitude of possible gaps. This theoretically claims the existence of a multiverse in which each void represents a different universe. Testing theories involving the multiverse and string landscapes is complex and often indirect. Physicists use a variety of strategies to explore these concepts. Detailed observations of the CMB are used to look for signatures that may be indicative of other universes, such as large-scale structure and cosmic anomalies, patterns resulting from bubble collisions, or changes in fundamental constants in different regions of the sky. Experiments at particle accelerators, such as the Large Hadron Collider, LHC, look for evidence of new physics predicted by string theory, such as supersymmetry or extra dimensions. Discovering such phenomena would provide indirect support to the string environment. Physicists are developing detailed theoretical models and running simulations to predict the observable consequences of the string landscape and the multiverse. These predictions involve specific patterns in the CMB or properties of dark matter that can be tested experimentally. Observations of high-energy astrophysical events such as gamma-ray bursts or black hole mergers could provide constraints on theories involving extra dimensions or gravitational changes predicted by string theory. It is crucial to ensure that string theory and its structure are mathematically consistent and compatible with known laws of physics. This includes stringent proofs and controls within the theoretical framework, as well as the ability of any proposed vacuum to produce physically habitable universes. While not a direct test, anthropic reasoning helps narrow down which gap in the string landscape might be relevant to our universe. By understanding the conditions necessary for life, physicists can make predictions about the possible properties of our vacuum and compare them with observations. The concept of the multiverse fundamentally changes our understanding of cosmology by suggesting that our universe is just one of many possible universes, each with its own unique physical laws and constants. This idea comes from the medium of string theory, which posits a multitude of possible spaces or configurations of the fundamental fields of the universe. The implications of this concept are profound. The multiverse provides a natural explanation for the fine-tuning of constants in our universe, such as the cosmological constant. In a multiverse with many different voids, it is statistically likely that at least one universe has the right conditions for life as we know it. Rather than requiring our universe to begin with highly specific initial conditions, the multiverse implies that a variety of conditions occur in different regions. The specific conditions of our universe are then seen as the result of a selection effect. We observe them because they help us develop observers. If multiple universes with different physical laws exist, it becomes difficult to predict certain outcomes based solely on our observations. Instead, predictions may need to be probabilistic, considering the range of possible universes. The anthropic principle, which states that the laws of the universe appear to be fine-tuned because only such a universe can support observers, is of greater interest in the context of the multiverse. The existence of multiple universes with different properties supports the idea that the parameters of our universe are not uniquely special, but are the result of anthropic selection. The search for a theory of everything, TOE, that unifies all fundamental forces and particles remains one of the most profound challenges in theoretical physics. String theory, with its concept of string landscape, offers a new paradigm that significantly influences the search for TOE. The string landscape expresses a multitude of possible solutions corresponding to different void states in string theory, each with different physical properties. String theory suggests a vast landscape of possible spaces, with predictions of approximately 10 to 500 potential solutions. Each void can have different physical constants, fields, and space-time dimensions. This implies that our universe is only one of a wide range of possible solutions. Busso and Polchinski, 2000. This diversity complicates the traditional goal of TOE, which has traditionally aimed to find a unique set of physical laws that govern all aspects of the universe. Instead, string theory suggests that multiple sets of laws may apply to different regions of a larger multiverse. The diversity of space in the string landscape may explain the broad range of observed low-energy physics events. Different cavities correspond to different effective field theories at lower energies and explain the diversity of particles and forces observed in our universe. This framework allows for a unified description of the different physical laws that govern various aspects of our observable universe. This landscape challenges the traditional goal of unification in TOE by suggesting that there may not be a single, unique set of physical laws that apply to all possible universes. Instead, unification can be achieved through a framework that identifies and connects multiple possible spaces. This perspective shifts the focus from finding a single universal theory to understanding the connections between various solutions within the string landscape. Moduli stabilization, the process of fixing the values of the shapes and sizes of extra dimensions, is vital in choosing which space to physically realize. This process influences the phenomenology of the resulting four-dimensional universe by affecting everything from particle masses to coupling constants. Effective module stabilization can naturally lead to a specific vacuum state that fits our observed universe. The string landscape suggests that some features of our universe can be explained by anthropic reasoning. The seemingly fine-tuned parameters for life can be seen as necessary conditions for the existence of observers like us, whose different values are realized in other parts of the multiverse. This anthropic perspective provides a potential explanation for the observed fine-tuning of physical constants and laws. The implications of the string landscape for the theory of everything are deep and far-reaching. String theory challenges the traditional notion of a single and unique TOE by offering a wide range of possible gaps. Instead, it proposes a more complex framework in which unification is achieved through understanding the connections between various solutions. The roles of module stabilization and anthropic considerations underscore the need to rethink our approach to combining and fine-tuning physical constants. As research continues, the string landscape will undoubtedly play a critical role in shaping our understanding of the fundamental nature of the universe. Thank you for listening. Stay well.